Hi, and welcome back to Codex. Today we have Dr. Ben Blum-Smith, who is a postdoc at Johns Hopkins. Dr. Blum-Smith is an expert in invariant theory and its applications to data science. Today, he will tell us about signals corrupted by cyclic group actions. Please take it away, Ben.
Thank you so much for inviting me. I'm excited to be here. Today, I'm going to be reporting on essentially two different projects, but one of them motivates the other. So the first half of the talk is based on joint work with Afonso Bandeira, Kileel, John Niles-Weed, Amelia Perry, and Alex Wein. The second half of the talk is based on joint work with Thays Garcia, Rawin Hidalgo, and Consuelo Rodriguez. The focus of my exposition is going to be on, like, the proof ideas are all going to be the proof ideas from the second half, but feel free, either during or after to ask me questions about the mathematical. I'm just going to tell you the results from the first paper. But I'd love to get into those proof ideas too, if you care. So I invite questions on the full spectrum of it. The structure of the talk is going to be, I'm going to tell you the story of the first work to motivate the key question being asked in the second work. I'm going to tell you the main results of the second thing, and then I'm going to get as deep into the proofs as we have time for. So I'm prepared to not tell you much of the proofs if we don't get to that, but I'm prepared to tell you much of the proofs if we do get to that. Okay. So here's the motivation. So the motivation comes from a class of signal processing problems, of which the paradigm example is cryo-electron microscopy, which is a biological imaging technique. And the way it works is you have a protein that you're trying to find out the molecular structure of. You have a sample of it that's frozen, and then you zap it with a powerful electron beam and you look at the images. And so the key features of this from the point of view that I'm trying to motivate mathematically is, one, that you don't know what direction you're looking at each individual molecule. So you have a huge number of images, but each individual image of the molecule is something where you don't know its orientation. So that's point one. And point two is that the images are extremely high noise. So the images on the right are giving you a little bit of a feel for this. So how we're thinking about this mathematically is, you've got a signal, which is the original protein shape of the protein you're trying to figure out what its shape is. You hit that signal with an unknown element of a group. In the case of cryo-electron microscopy, that group is the three-dimensional rotation group. And then you add a ton of noise to it. So in the general setup, you have a signal, which we're going to think of as just an element in a vector space, potentially a high-dimensional vector space. And then you've got, so you've got your signal, you've got your noise. Yeah, I think at least so far I'm being consistent with the color coding in the title slide. So blue means signal, purple means noise, and green means a random group element. And then you hit, in either order, because the actions commute, you hit it with a group element drawn uniformly randomly from some compact Lie group. So then what you see in the end is the transformed signal plus noise, which we're separating into a direction component drawn from a normalized Gaussian, and then we scale it by a noise level, which we're going to think of as something we can control, although it's fixed throughout an individual instance of the problem. So an individual instance of the problem has a fixed signal, a fixed noise level, but then every individual sample that you see of the signal, you randomly draw the, from a normalized Gaussian, and you randomly draw from a uniform distribution on a compact group, and then this is what you witness. Transformed signal plus noise, scaled by the noise level. Good so far? Okay, so the goal is to estimate the signal. There's no hope to do better than to estimate it up to its orbit under the group action, because you hit it with a uniformly random group element. So as soon as you did that, you destroyed any information about where it was originally in its orbit. In the case of the molecule, the motivating example of cryo-EM, you really don't care what the orientation, you want to understand the structure of the molecule modular orientation. You don't care about the orientation, and you will never see the orientation because they're different for every signal. So, for every draw of a sample. So when I say estimate theta, I don't mean estimate theta. I mean estimate theta's orbit up to translation by the group. The real research question that I'm going to be focusing on is how many draws of a sample does it take before you can get an accurate estimate? Now note that, like, if there's no noise, one is enough, right? Because this, if this term is 0, then this term fully determines the orbit. So it depends on the noise level. And the real question that I'm going to be addressing is, how does it depend on the noise level? What is the relationship between scaling up the noise and how many samples you have to see before you can accurately estimate the signal, which is known as the sample complexity. So this is my first, this is my first reporting of a result that I invite questions about the intuition behind and/or proof of now or later. But this is from the first collaboration that I mentioned. The theorem is that the number of samples that you need in the high noise regime scales with the variance to the power, the variance of the noise to the power of the minimum degrees of the polynomial functions on the original vector space that are invariant under the group action and that are able to distinguish that orbit from other orbits. Did that make sense? So, like, if, in a typical situation, like, for example, if the action of the group on the original vector space is irreducible, then there will be no degree 1 invariant polynomials. So the D here will definitely be at least 2. Because there's no hope to distinguish this orbit from other orbits using invariant polynomials of degree 1 that don't exist. So, but if it turns out that your orbit is pinned down by the values of the invariant polynomials of degree at most 5, then you can do this with sigma to the 10th, order of sigma to the 10th samples, where sigma is the standard deviation of the noise. So again, I invite questions about that result, but I'm not going to be dwelling on it. But it's the key thing that you need to know for what I am going to be dwelling.
I'd like to ask a question if I can.
Yes, please.
So when you say this is the number you need, are you saying, like, there's some abstract map that takes the data I receive, or that takes the original signal and then produces the data that I receive, and it's like that that map isn't going to be injective until this point? Is that what you mean?
Okay, so that's a beautiful question. There might be a way to formulate it in those terms, but I don't think it's the right way to formulate it because it's really a probabilistic statement. So, so the right way to think about it is, can I, or at least I don't want to say that, I don't want to be overly prescriptive, but how I am thinking about it is, and I also want to add the asterisk that if you know John Niles-Weed, he's really the person on the team who's, you know, who's the deepest in this result. So, you know, if I can't satisfy you, then you should talk to John, but I'll do my best. So the statement is that, you know, we fix like some range of magnitudes that sigma is going to live in, because we want the noise level, sorry, sigma, theta, that theta is going to live in, because we want the noise level sigma to reflect the noise level. So we need a little bit of a bound on the magnitude of the signal, you know, so just fix theta between, you know, a minimum norm and a maximum norm, just to allow sigma to actually reflect the noise level. Am I making sense so far?
Yes.
So within that, you know, kind of annulus type thing of signals, the question is, does there exist an estimator for sigma that can succeed with some fixed probability, meaning that can be such that the value of the estimator is within some epsilon of the value of the orbit of sigma.
Hold on, you keep saying orbit of sigma. You mean orbit of theta?
Theta, yes, I apologize. I keep saying sigma when I mean theta. That's happened at least twice now. Right. You want to know the orbit of theta. The goal is to know the orbit of theta. You're not gonna do better than an estimate, because what you see involves noise. So what you want is something that you can compute based on the data that you observe that is close to theta with high probability. And the statement is that an estimator that is close to theta with high probability doesn't exist based on fewer than this many samples. But that with this many samples, you can build an estimator that is close to theta with close to the orbit of theta with high probability. Have I answered your question?
I think so, yeah. I'm
awesome. Thank you for the question.
I have another question, but I don't want to interrupt your talk anymore. Please continue.
Okay. Please ask me the question later. Okay, so the reason that I shared this theorem with you is because of the way it motivates the following question. In general, it highlights our attention on the question of, in general, how big does the degrees, do you have to make the degrees of polynomials before the invariant polynomials of those degrees can see the difference between your orbit and another orbit? So right, so before I move on to the next slide, I'm pointing out that the theorem that I gave you on the previous slide motivates this purely algebraic question. So this result on the previous slide is a result in statistical information theory. But it motivates this question in pure algebra. So from this point on in the talk, unless you want to ask me more questions about the result on the previous slide, which again I welcome, is how big degrees of polynomials of polynomials invariant under the action of the group. How big do you need to make the degrees so that the polynomials, invariant polynomials of those degrees, are able to distinguish orbits? And this is an area where there exists some classical results. So the first of these that I'm going to mention is this theorem from the 50s in the context of pure, algebraic geometry and the study of algebraic groups, which is that invariant rational functions distinguish almost all orbits if and only if they generate the field of invariant rational functions. So for those of you whose background is not coming from algebra, I'm going to tell you what this means. This means that the invariants separate almost all orbits, and by almost all, I mean all of the orbits away from a closed measure zero subset. Specifically, a Zariski closed subset, if that means anything to you. If and only if an arbitrary invariant rational function of the coordinate functions can be written as a rational function of these specific invariants. Did that parse? So this gives us a dictionary between separating one good kind of separating property. Now it would be even better if they uniquely identified every orbit than if they just uniquely identified every orbit away from a measure zero subset. But what we're going to see going forward is that you can, since the statistical information theoretic result that I mentioned before means that the sample complexity of your signal processing problem is scaling exponentially in the degree of the polynomials you need to achieve your separation task. So that means that if you can relax your task a little bit and save a lot of degree, that's worth it probably. And what we're going to see is that there's a huge gap between the Fs that you need to uniquely identify every orbit and the Fs that you need to do the thing that's on this slide, which allows you to uniquely identify almost every orbit. So that motivates an understanding of the Fs that do this latter thing, because they're going to really save you a lot of sample complexity in your original signal problem. So I'm just as an aside, I'm going to be working over C for the rest of this talk, but the information theoretic result that I mentioned before is over R. And over R, it's the case that if they generate the field of all rational functions in the sense of the bottom half of this slide, then they do separate almost all orbits. But the converse is not true over R, and the reason for this is basically just that generating the field is kind of insensitive to whether you're over R or C. If the representation is defined over R in the first place, if you're acting on a real vector space in the first place, then the bottom half of this is the degrees that you need to go to have Fs that do what's in the bottom half of this don't depend on whether you're working over R or C, but it's a stricter thing to separate almost all the orbits, period, from separating almost all the real orbits. You could potentially separate almost all the real orbits without separating almost all the orbits on C. And just as an example of that, if there's no group action acting on a single copy of the complex numbers, then every polynomial is invariant. And x cubed separates all the real orbits, but not all the complex orbits. Right, because the cube root of you can take the cube root of a real number in a unique way, but you can't take the cube root of a complex number in a unique way. So if that, it's not important that the things that I'm saying right now land. I'm just illustrating the pink in the bottom of this slide about how the good separation property is implied by the good algebraic property of field generation over R. So it's still interesting to know the answer to this question over R, and it's still relevant to the signal processing problem, but it's not the complete story over R that it is over C. Okay. Again, questions or? Okay. So the point of all that is that it motivates us to study the following strictly algebraic question. How big does D need to be such that any invariant rational function of the coordinate functions on your original vector space can be written as a rational function of invariant polynomials of less than or equal to that degree? So I think this is a great, great algebraic question that's very well motivated by the signal processing application. And I'm going to tell you that the analogous question for polynomials, meaning instead of asking for rational functions to be expressed as a rational function of these particular polynomials, just to ask for all polynomials to be expressed as polynomial functions of these polynomials. That's a classical and very well studied question. With the foundational result being Emmy-Noether's theorem from 1915, that if the group that's acting is finite, then you can always do it with polynomials of degree less than or equal to the group order. Meaning any polynomial invariant can be represented as a polynomial in the polynomial invariance of degree less than or equal to the group order. That bound is rarely sharp, but a place where it is always sharp is the cyclic group of prime order. So if you have any non-trivial group action by the cyclic group of prime order on a complex vector space, then you have to go all the way up to the order of the group polynomials before you can generate all the polynomials from the invariance, all the invariant polynomials from the invariance of degree less than that. Whereas in contrast, even for this simplest of all groups, the question about field generation is interesting. And I am going to illustrate this with an example. So let's take P equals 11. So we're going to have the group be the cyclic group of order 11. We can specify the action of this group on a complex vector space just by specifying the action of its generator. So let's take the generator and say it acts on a complex vector space C3. Really there's a technicality I'm going to sweep under the rug here, which is that there's intellectually a difference between its action on the original vector space and its action on the functions between the vector space they're dual to each other. So, but I'm just going to write down the matrix for its action on functions because we're going to be analyzing functions and invariant functions. So let's just specify the action of the generator on the functions, and the action on the original C3 will be the complex conjugates of these three numbers just by duality. But anyway, we're going to act with a primitive 11th root of unity on X. We're going to act with the square of that primitive 11th root of unity on Y. And we're going to act with the 7th power of that primitive 11th root of unity on Z. Sound good? Okay. So if we do this, then the 11th powers are certainly invariant because the 11th root of unities wash out. But there are no invariants of degree less than 11 that are polynomials in X or Y or Z alone, because every non-trivial 11th root of unity is a primitive 11th root of unity. So, a power of X or Y is not, when you hit it with the generator, then it's going to be multiplied by that power of the root of unity, and it's not unity unless that power is a multiple of 11. So because of that, if you attempt to write these three invariant polynomials as polynomials in invariance of degree lower than that, you can't do it, because all of the lower degree invariants have they don't just have x or just y or just z in them, they have more than one variable. So if you make a polynomial in that, you're going to still have more than one variable. So this just illustrates that complete algebra generation, meaning polynomial generation of the invariance by the invariance of low degree is not possible below degree 11. And as an aside, I'll mention that it's also, I'm not going to go into why, but it's also impossible to uniquely separate every orbit, to uniquely separate worst case orbits with polynomials of degree below 11. On the other hand, if you allow yourself division in combining your generators of low degree to try to get the rest of them, then you can do it in much lower degree. So here I have taken three invariants, and I just want to point out why they're invariant, right? Because x is acting by one, just the primitive 11th root. This y is being acted on by the square, z is being acted on by the 7th power. So x squared times y times z is being acted on by two of them here, one of them here, and 7 of them here. Sorry, 2 of them here, 2 of them here, because y is acted on by the square, and 7 of them here. And 2 plus 2 plus 7 is 11. So this thing is invariant. And likewise, y squared, this gets acted on by 4 of the roots of unity, and z, this is a z. It looks a little like an x, but it's a z. This is being acted on by the 7th power. So there you go. That's 4 plus 7 is 11, and likewise 7 to the 7, the 7th power of root of unity to the 3rd power is 21, and then x is one more. X gives you one more, so 22 is again a multiple of 11. So these are all invariant, and look, I can express the things that I couldn't express before as ratios of powers of them. So here I've got three polynomials whose degrees are at most 4 that are able to generate the field of rational invariance as a field, and that means, by the theorem that I mentioned above, that they can generically separate orbits. There's a measure zero closed subset of bad signals on the complement of which these functions uniquely identify all the orbits. So that means that if you want to do the worst case signal, you're going to need standard deviation to the 22 samples order of that to get a good estimator. But if you're willing to throw out the signals where these don't uniquely separate orbits, then these ones can do it with just sigma to the 8th, which is like still probably terrible, but way better than sigma to the 22nd. Making sense so far? So now I'm going to talk about the methodology that we use to study the question. So before giving you some results. So the general question is focusing attention on Z mod P. Some of our results are more general, but our main line of inquiry was just focusing on it because the story is already interesting. You know, I hope to have convinced you on the last 2 slides that the story for Z mod P is, even though it's not interesting in the classically studied question, that it's interesting in the question that where you're generating rationing and not just as polynomials. So, okay, so the general setup is here's Z mod P. acting on some complex vector space, there exists a way to diagonalize the action, right? So this is a basic fact of linear algebra. I can take the generator and I can just find a basis for C to the n such that the action of that generator is by a diagonal matrix. And then because this thing has order P in the group, the matrix by which it acts has to have all Pth roots of unity on the diagonal. Let's introduce some notation. So I'm going to say M is the number of distinct non-zero classes, residue classes mod P among these exponents, which are the exponents of some fixed primitive Pth root unity that we're with reference to. So M is the number of distinct numbers that appear along this diagonal. And beta field is the number of interest. It's the minimum degree such that the invariants of degree less than or equal to that degree generate the field of invariant rational functions in terms of multiplication and division and subtraction. Okay, so now I'm going to give you results and then we'll do as much proofs as we have time for. Sound good? So the first is a lower bound. It can't happen in degree lower than the nth root of P. That's a hard lower bound. And this bound is sharp. And here's an upper bound. It can't happen in degree, if M is less than 3, it might have to, depending on the specific way that the generator acts, which is to say, depending on the specific numbers A that go here, you might have to go up to degree P. But if M is at least 3, you don't have to go up to much more than degree P over 2. So this is our theorem. This is not sharp. The lower bound is sharp, the upper bound is not sharp. We think that the real answer is this. So ceiling of P over ceiling of M over 2. So it drops as M grows. We have strong numerical reasons to believe this based on computations. And we can exhibit a specific representation of Z mod P that achieves this bound. So if it's correct, then we know it's sharp. But this is for now what we've proven so far. We have some more detailed results when M equals 2, meaning that there are exactly 2 distinct numbers on this diagonal. In that case, define B to be the positive number that represents the ratio between these exponents mod P. So this is uniquely defining B. B can't be 1 because these numbers are distinct. So the ratio between the mod P is not 1. But because every residue class mod P is invertible, there is some number B that allows you to multiply one and get to the other. I should have said distinct non-trivial. I don't know if I said distinct. Yeah, I said distinct non-zero, but right. We can throw out ones that appear on this thing where the A is 0. So, all right. So with that definition, B is the ratio between the two. Basically, what power you have to raise one of the roots of unity to get the other root of unity on the diagonal. If you define B that way, then we also have the following. So if B is anything other than P minus 1, this is the case of 2 distinct characters. So you can actually, the bound of P is sharp here. But if B is anything other than P minus 1, then we have the same bound we have for when M is at least 3. And actually, this is a key lemma for the general result. Also, we have a formula that's an upper bound that this upper bound holds all the time, but it becomes an exact formula under some easy to verify conditions. So basically, if you divide the prime that you're working with by the B ratio between the characters using Euclidean division, then if the ratio is sufficiently high compared to the remainder, then this inequality is equality. So this inequality holds all the time, depending on that representation. And it's actually an equal sign if Q is sufficiently big, depending only on R. And if if B is sufficiently big compared to R, then all you have to do is have Q be bigger than R, and it's also equality. So those are the results. And now I will talk about methods. So let me take a pause to take questions before I dive into methods.
Yeah, let's see. I'm not on video, but this is Dan Edidin. Hey Ben.
Hi, you are on video.
Did my video come to life? Okay, I wasn't on video before because
yes,
I'm really like, don't want to have people see me picking my nose, stuff like that. But anyway, so I'm looking at this and I'm actually thinking about torque varieties, like these configurations, like of these weights give us different, affine torque varieties with different, so is there any kind of toric picture that you can associate to these sorts of representations?
That's a great question. I'm sure there is, but I haven't given it any thought. So I can't really answer the question right now. But I'm 100% sure, yes, I feel 100% sure. Like the invariant rings here, as I'm about to demonstrate in the next few slides, are normal affine semigroup rings. So I just feel like all of that toric geometry stuff is hanging out here somewhere.
Yeah, well, yeah, certainly, yeah. If you've seen it, right, you think, there might be some pretty picture, like when you need lower degree, it says something about, the rays generating this, because all you're doing is generating a cone, in fact, right? It's just a single cone, right? With these, because we're affine torque varieties, and so, but it's saying something special about the cone and other situations.
I think that's like absolutely a worthwhile thing to think about that I haven't really thought about.
Okay, sure, thanks.
Awesome. Okay. Other questions before I go into the methods? Okay. So, all right. So the key point, I'm going to summarize the overall before I dive into details. The overall point of these next few slides is that because we've chosen a basis to work in which the action on functions is diagonal, meaning that each indeterminate just gets multiplied by something. Therefore, the action on monomials is diagonal, like each individual monomial is an eigenvector for the action on functions. And it is possible, and I won't go into the details of this, but it's because it's basically algebraic bookkeeping, but it's possible to show that the question of generation of the field by, meaning the expressibility as rational functions of your chosen generators, all comes down to the set of invariant Laurent monomials, rational monomials, monomials with possibly negative exponents. And these form a Euclidean lattice because they're a subset of, they're a subgroup of the just group of Laurent monomials, which is basically in natural bijection with integer points in Zn. Integer points in Rn. So the invariants essentially form a sublattice of the integer lattice. And we can study the question that I've put in front of us by studying that lattice. So here are the details, right? What's the condition on a monomial that says that it's invariant under this group action? So the group acts. Oh, I was maybe going to write this out, right? Just for satisfaction. So the group acts. You know, one sends X to zeta to the A, X, Y to zeta to the B, Y, and Z to zeta to the C, Z. So what happens to X to the A, Y to the B, Z to the C? It gets sent to zeta to the A, X to the A, zeta to the big B, little b, Y to the B, zeta to the big C, little c, Y to the C. So this is invariant if and only if zeta to the A plus B plus C equals 1, which is the same thing as that the exponent is 0 mod P. So the condition on a monomial that says that it is invariant is this sort of linear equation mod P. So this gives us a lattice of integer points that satisfy that condition. And I've drawn that lattice. I've drawn the positive orthant of that lattice for the specific case of A equals 1, B equals 5, C equals 6, and P equals 7 here from 2 different angles, just to show you what it looks like. So to me, this is like, on some level, this is a picture of the invariant ring. So the positive orthant is the ring, and the whole lattice in all of 3 spaces is the field. And again, this is the algebraic bookkeeping I was mentioning. I am happy to talk about methods here, but it's sort of a annoying but routine verification that the lattice is generated by points up to a certain degree, where the degree of point means the degree of the corresponding monomial, if and only if the polynomials up to that degree generate the field. So that somehow the addition and subtraction involved in field generation are not like the important thing going on. The important thing going on is, can you get the monomials from these monomials by multiplication or division? So once we know that, that means we can study the previous question by restricting our attention to Euclidean lattices. So we just want to know, like, does this little corner that I've drawn, you know, this little triangle here, is the plane sum of the coordinates equals a little bit more than 4. So this is showing you, on one side of it are all of the lattice points in the first orthant, so meaning they're honest polynomials, you know, honest monomials, whose degree is less than 4, less than or equal to 4. And everything else is higher degree. And so because these 3 little ones that are here, the only 3 non-zero things of degree less than 4, nonetheless form a basis for this whole lattice. Therefore, that's the fact that the lattice is generated by points of degree 4, i.e. the corresponding invariant field is generated by polynomials of degree less than 4. Okay, so that's the method. And then now that that basic method is set up, I can show you the proof of the lower bound. Do I have time for this? This proof is actually pretty quick. I probably won't show you the other proof.
You have a few minutes, yeah, you're fine.
Okay. So I want to convince you that it's impossible to generate this lattice by points in the first orthant whose sum of their degrees is there's no difference between greater than and greater than or equal to here because we're assuming P is prime. But actually, this theorem holds in a much more general way that applies to any finite abelian group. And actually, we have a generalization using different methods that applies to any finite group. But in the more general case, this can have equality. But that's sharp. But anyway, what I have to convince you is that it can't be done with points that are less than root m of the group order. So I'm going to argue the even stronger statement that there do not exist dimension many linearly independent points whose degrees are all smaller than this. And the argument is this. So I'm going to work it out in the dimension equals 2 case. And the lattice I have illustrating the situation is a plus 3b equals 0 mod 7. But the argument works without change, essentially, in higher dimensions. So I gave myself a copy of the slide just so I can mess up the copy without losing the original. Okay, so here's the point. Imagine yourself with 2 points, 2 linearly independent points. My claim is going to be that one of their degrees at least is bigger than the number on the bound at the top. Okay, why do I think this? Well, the first point is they're linearly independent, so they generate a 2-dimensional sublattice of the integral lattice. That sublattice, if these points are themselves invariant, meaning they satisfy my equation, then they generate a sublattice of the invariant lattice. In the case that I've drawn here, they're actually literally a basis for the invariant lattice, but in the worst case scenario, they generate a full rank sublattice of the invariant lattice. Now, I claim that the invariant lattice has index equal to the group order in the whole integer lattice. So you can see that in this picture. I've sort of illustrated that in this picture. The invariant lattice is the blue points. Can you guys see the colors? Should I make it bigger?
I can see it.
Let me just, why not? I can, so why not? So the blue points are the invariant lattice. And each of the other colors / whether it's filled or not is giving you one coset of the invariant lattice inside the integer lattice. And there are 7 because this equation is mod 7. And so any A and B such that the left side of this equation adds up to anything that's not 0 mod 7 is going to be a residue class mod 7 that generates all the residue classes mod 7. So all 7 residue classes mod 7 have to be possible. And that means that there are 7 of them. Those are the 7 cosets. So I know ahead of time that the number of cosets of the invariant lattice inside the whole integer lattice is the group order. And I know that the lattice that I generate when I pick 2 linearly independent points is contained in the invariant lattice. So its index in the integer lattice is going to be at least that big. So what I have is that the group order, which is P in this case, is less than or equal to the index. Let me do this in 2 steps, like I just said. It's equal to the index of the invariant lattice. And that's less than or equal to the index of the lattice generated by my 2 points, which I'll call A1 and A2. With me so far? Okay, so now I use a sort of classical fact that the index of the integer lattice, the index of a sublattice of the integer lattice inside the integer lattice is equal to the area of a fundamental parallelogram for that sublattice. So this last thing here is equal to the area of the parallelogram spanned by my 2 points. And well, what's that area? Well, that area is, what do I know about it? I know that it's at worst the product of the lengths of the 2 points. It's at most the product of the lengths of the 2 points, right? This is called a Hadamard's inequality. It would be exactly equal if they're orthogonal. You all agree? And meanwhile, by the triangle inequality, the L1 norm in a finite dimensional real vector space is always an upper bound on the L2 norm. Do you agree with me? This is just essentially the triangle inequality. So that means that, and the L1 norm of the points in this scenario, the points correspond to exponents, to monomials with the given coordinates as exponents. So the L1 norm is the same thing as the degree, if the monomial is an honest monomial. So where by degree of a point, I mean degree of the corresponding monomial. So this string of inequalities, and by assumption, whatever the generation degree needed to generate the lattices, it's at least as big as the degrees of two linearly independent points. I mean, I say two because I'm working in the dimension 2 case, but this argument is easily adapted to an arbitrary dimension. So just putting this string of inequalities together and taking the square root, I get this. Boom. Or taking the mth root in the general case. I guess there's one thing I didn't mention, which is why, because I've stressed that m is the number of distinct non-trivial characters in the action. So the number of distinct non-trivial things on the diagonal of the matrix by which one acts. And to get that, I need to do something which I realize I left out of the slides, which is that it doesn't matter. It does not affect this number if you delete trivial characters or if you merge non-trivial but equal characters. So in the case where I'm acting on a 17-dimensional vector space, but there are only two non-trivial, distinct non-trivial things on the diagonal of that matrix, m is 2, but the dimension is 17. So you might think, why am I not taking the 17th root here? And the reason is because the right side of this won't change if I replace that action with an action that only has one copy of each of the two distinct numbers, non-trivial numbers, and no copies of the trivial number. So the left side of this doesn't change in that case. And then I can do this whole thing working in dimension 2. So that's that one. Okay, that completed the proof, and I ran a little over time. I apologize about the tech things. So I feel like I shouldn't tell you any other things, and I should just I should let you take it from here.
Okay, let's thank our speaker by clicking buttons.